Mathematica is the ultimate computation platform that is well suited for the rigours of many different fields. Over the past 20 years, Mathematica has been adapted by everyone, from academics drafting papers to programmers writing software, from traders creating financial models to scientists analysing experimental data. And today, developers at Wolfram Research, makers of Mathematica, are continuing to develop the software to make it even more useful and intuitive for your every need. In this talk, I will try and illustrate Mathematica to you quickly by showing 7 fairly different examples. From finance, I'll try and optimise risk across some investments. I'll walk you through an application for extracting information from microscopy images. We'll try and create an algorithm to keep an inverted pendulum upright. My statistical example will estimate the power that a wind turbine can generate. And for less structured data, I'll make a website crawler and extract information about the site structure. Then, I'll denoise some historical sound, and at the end, we'll have a little fun with making an animation. Everything I will show you will be tasks that Mathematica can do right out of the box. No add-ons, no extra toolboxes, no additional downloads. Our first example will be to show how you can use Mathematica in finance to pull stock prices and run some simple but useful tasks. For many people, Mathematica is an interactive exploration environment, where you work by typing questions and getting answers. And the easiest way to do that is to use linguistic queries made available by the integrated Wolfram Alpha functionality. Wolfram Alpha is an award-winning knowledge engine with more than 1 trillion unique data points. You can pull up data on everything from the beef production of the UK to the 3D chemical structure of caffeine. The possibilities are endless, and they're all accessible directly from within Mathematica. But for this finance example, I'll begin by asking Wolfram Alpha for stock performances, say on Apple. Amongst various other data, here's the past price performance, and I'm going to pick the last 5 years. And then I can obtain the actual data by selecting the computable data option from the output pod. That also gives me a formal way to ask for the same data. I can use that as a template, also to ask for data on AIG. Mathematica provides lots of capabilities for transforming and rearranging data. So matching up the dates present in both data sets and then pulling out the corresponding price values only takes a couple of lines of input. And most of the input for visualizing them is specifying the labels. You can see that the price history of these two stocks is very different. This is why the paired histogram shows a big difference in their price distributions. I can now calculate the continuously compounded return on the two stocks using this function that I've just created, and visualize it straight away. Surprisingly, with such a dispersion in stock price distribution, the daily returns distributions are almost identical. Small but negative compounded return does make a big difference to AIG's stock price. Since investors tend to hold more than one stock in their portfolios, we might want to measure the correlation between the two stocks. And we can also visualize the correlation of the two stocks. Notice the R squared is the correlation squared. Since the correlation coefficient is less than 1, we have a combination of imperfectly correlated risky assets. The implications of this fact, for risk, is central to an understanding of the effects of diversification. Say we have some attributes such as the expected return and standard deviation about two assets, we can construct a hypothetical model to show their performance in terms of the standard deviation of the portfolio. And to make it easier to understand, I've constructed a little interface to allow easy exploration. The blue line is where the efficient frontier lies. It represents the edge of the feasible combination of risk and return. When the correlation between these two assets is 1, there's no risk reduction. As the correlation decreases, we can achieve a portfolio with the highest expected return for the lowest standard deviation. Therefore, a small correlation is a strategy for diversification, and that is of course what investors are trying to achieve: low risk, high return. This model turns out to be the foundation of the famous CAPM model that is widely used in the financial industry today. Well, how does Apple and AIG compare with the hypothetical model? Well, if we use the historical returns as the basis for their expected future returns, then we get this. A portfolio with just Apple and AIG, the expected return is lower. Of course, this example leads into what is known as asset allocation. And if you're interested in this topic, You might want to check out some nice demonstrations of this by Jason Corley and Roger Brown at demonstrations.wolfram.com. The next example is focused on image processing, but also shows that Mathematica can be used as a development environment to create applications for deployment to people who have no desire to know how Mathematica works. The task is to analyze the performance of needle-free injection devices that fire powdered drug particles into the skin on a supersonic gas shockwave. We're trying to understand the penetration characteristics on a test medium by photographing thin slices of target under a microscope and measuring the locations of the particles, as shown here. The challenge is to do a good job of identifying the particles and to give manual override for any mistakes. It all has to be packaged up in a neat point-and-click interface ready for deployment to users. A pretty typical software development task. The task really breaks into three parts. First, image processing. Second, an optimal graphic user interface for interaction. And third, the analysis and report generation. Step 1 seems like it should be the hardest, but can be achieved in very little code. Here's a detail from a typical image. First, I need to clean up the image by deleting all this dirt and texture. The command delete small components will remove small white dots from within the particles. And then inverting and doing it again with a parameter lets us delete large black components up to the parameter size. Once cleaned, we need to erode the components back to a single point. But we need multiple components that slightly overlap to break and erode back to separate points. This is called ultimate erosion and can be done using max detect on the distance transform. We can then use component measurements to get information on these points, in this case, the coordinates of the centroid of each point. Well, here are all of those steps packaged up into a neat little function. The hardest part is the graphic user interface. Hard because I want to give lots of control. Here's the video of the application that I want to make in action. This is a Mathematica-based tool for analyzing microscopy images. You start by asking it to load an image. You tell it which image you want, and it displays the image together with white crosses showing the particles that it has identified. You can scroll through large images and resize the image area to see more. There are advanced settings for the automatic detection. Reducing the minimum particle size or minimum particle separation makes it more sensitive. These controls are hidden by default. There is a manual override for the identification. You can remove crosses, add crosses, and also move crosses where you think that it has missed or misidentified particles. There are sliders at each side that allow you to manually align the cyan line with the surface of the slice of target, often too faint for automatic detection. Then you get an automatically generated report, which shows that it has identified 260 particles. It gives you visualizations of their spread profile, depth profile, average depth across the sample, and the coordinates of each of the points identified. And now here is the entire code for that application. With the image processing, report generation, data analysis, and user interface, it amounts to about 30 lines of code. And I'll talk you through that. First, I want the GUI to be in a palette of its own, not in a notebook. But I want multiple instances of it to be able to be opened at once. So my code starts by creating a palette and localizing variables into the window instance, not globally into the Mathematica session. The main guts of the user interface is then just to manipulate, just as we saw earlier. The first calls the identify blobs command that we just created, and then displays the results. And then we just list some of the user interface elements that we want, a couple of buttons, and an opener view that hides the advanced controls, and the various sliders listed together with their default values and the parameter which they change. After the half dozen lines or so that describe the user interface, we get the definition of the function that we developed before, and then comes the report generation. Mathematica provides a complete document description language, so all I have to do is to describe the layout and style of the document in terms of the individual components. Here we have a text cell containing a title, some more text giving the output, and various charts. Evaluating the code creates the application, which I just save and send to the users. They don't even need a full Mathematica to use it. It will run in the runtime application Player Pro. The next example, by Wolfram researchers Andrew Moylan, has its place in engineering. We will be using Mathematica to simulate an inverted pendulum. You've probably seen one in a Segway. Mathematica is full of all kinds of powerful solvers, from integration to recurrence relations and optimization to graphs. In this example, we'll model a single inverted pendulum on a moving cart, shown here. We'll use the differential equation solvers to model it, and then stabilize it using control system solvers. First, we need to simulate the pendulum and cart system, and then we can try to determine the control force, F of t, that will move the cart to keep the pendulum balanced upright. Assuming the pendulum arm is uniform, so its centre of mass is at d/2, and ignoring friction, and using dimensionless units in which the gravitational acceleration constant g equals 1, the model pendulum and cart system shown above satisfies this pair of differential equations. Let's explore the concrete case where m, c, and d are all 1. We can enter the equations into Mathematica directly, almost exactly as they appear in the textbook. Using NDSolve, Mathematica's numerical differential equation solver, we can immediately simulate the system from a slightly off-center initial condition. We're going to use theta of 0 is pi/2 minus 0.1. We will initially use no control force, so f of t equals 0. That is, we make no attempt to move the cart to keep the pendulum upright. Here's an animation of the solution. The animation code is included in the download notebook. As you can see, it's not very stable. We can combine the above two steps into a handy function that animates the control system for any control force f of t. We can then use this simulate pendulum function to explore ideas for keeping the pendulum balanced upright. The simplest plausible idea that I can think of is to push the cart in whichever direction the pendulum is currently leaning, moving the cart under the pendulum to stop it falling over. The pendulum is perfectly upright when theta of t is equal to pi/2, so let's try pushing the cart with a force of pi/2 minus theta of t. Well, you can see that stopped it falling over, but it's not stable, it's oscillating from side to side. Maybe we can make it smoother by taking into account how fast the pendulum is falling, which is theta prime of t, the first derivative of theta. Well, that stopped it wobbling nicely, but now the whole system is coasting steadily off to the right. What if we want the cart to stay at the point, say, x of t equals 0, in the centre? Well, we could go on modifying the control force by hand and try and get a working solution, but it's much easier to turn to Mathematica's new control systems design features. We want to keep the state of the system near the unstable equilibrium point of x of t, x prime of t, theta t, and theta prime of t at 0, 0, pi/2, and 0. The equilibrium is unstable because in the absence of any control force, small deviations from this point tend to get larger. The handmade control forces we tried before are special cases of linear control, in which the control force is some constant linear combination of the deviation of the states from the equilibrium point. The constants ki in this equation are called feedback gains, and we can use a couple of new control theory functions in Mathematica 8 to find good values for them. We begin by constructing a linear model for the behavior of the system near the equilibrium point. The function state space model does this automatically if we give it the nonlinear equations from before and the values of the equilibrium point. The result of the state space model looks like an augmented matrix. Its columns describe the effect of small deviations of each of the state variables, x of t, x prime of t, and so on, from the equilibrium. For example, the third column says that near the equilibrium point, small deviations in theta of t away from the upright position, which is theta of t equals pi/2, lead to an increase both in x prime of t, the speed of the cart, and theta prime of t, the rate at which the pendulum is turning. The augmented fifth column similarly describes the immediate effect of the control force on the state variables. Now that we have a model for this system, we can use the function LQ regulator gains to find the values for the feedback gains ki. In the second argument of LQ regulator gains, we specify the following quadratic cost function for the system. LQ regulator gains finds the values for the constants ki that minimize this cost function over time in the linearized model. The cost coefficients 1, 10, 10, and 100 are a guess, based on an intuition that the deviations in theta prime of t are relatively more important than deviations in x prime of t and theta of t, which in turn are more important than deviations in x of t. Different coefficients would give better, worse, or just qualitatively different behavior. In real life, the coefficients might represent actual costs associated with the deviations of a system from its desired state. Using these gains, our control force is this. Well, let's test it out. Well, that seems to do a pretty good job. Our pendulum stabilised via LQ regulator gains can survive some quite bumpy conditions. Here's a function to describe the bumps, and here's the simulated result. If you bump it hard enough, the linear control system we've used here won't be able to recover. You can try that out by downloading the CDF file for this talk. Another natural thing to explore would be the effect of different cost functions in LQ regulator gains. It's also fun to try to design your own superior control force by hand for this relatively simple system. What can Mathematica contribute in the field of sustainable energy? Well, it turns out, with a combination of built-in data and extensive statistical functionality, Mathematica can quickly make some headway. In this example, we use information from the built-in weather data and investigate the feasibility of using wind to generate electricity for central Illinois. First, we'll get the average daily wind speed for the weather station nearest to Bloomington, Illinois. We can see that the form of the data is ordered pairs consisting of the date and the average wind speed for that day. And a quick plot reveals some obvious periodic trends. We don't care about the date information, so I'll extract out the second part of all of the data points, that's just the speed part, and at the same time convert from kilometers per hour to meters per second, and we'll visualize a quick histogram. Since wind speed can be assumed to vary continuously, we can represent the distribution for the observations using the smooth kernel distribution. And I can visualize this distribution together with the original histogram. We can immediately ask questions of this distribution. For example, what's the probability that the average speed on a day will be above 3.5 meters per second? However, I'm going to assume that the data really follows the extreme value distribution. Now, Mathematica contains support for more statistical distributions than any other system, so it's straightforward to estimate the parameters if it does follow this particular distribution, and also a symbolic representation of that distribution. Now let's see if our assumption should be rejected. So according to this hypothesis test, our assumption should not be rejected, and here's the p-value for that test. So now that we're happy that it was a reasonable assumption, we can visualize our distribution estimate. The electricity generator that we are going to use for our analysis here requires 3.5 meters per second of wind speed to generate electricity. We can use the probability function that we saw before to estimate the proportion of the time that the generator will be contributing to the grid, which is 72% of the time. And here's a quick visualization of that. From the manufacturer's spec sheet for the V82 1.65 megawatt generator, we can make a chart indicating anticipated performance levels in the central Illinois location using these calculated probabilities. The expected electricity contribution is just the total expectations of each interval, which in turn are the probability of that interval, using our estimated distribution, multiplied by the electricity contribution that that interval will make. So on average, we can expect 0.4 megawatts out of this generator. Now let's turn back to Wolfram Alpha data and ask how many hours in a year, and also the retail price of electricity in that part of the world. Multiplying that together, and adjusting for dollars versus cents and megawatts versus kilowatts, we find that each generator would produce $439,000 worth of electricity each year. One strength of Mathematica for data analysis is the ability to hold information in complex structures without having to try and force it into an array. Here, I've implemented a web crawler from scratch. At its heart is a function nestlist, which recursively applies a function accumulating output as it goes. The start point is a root URL parameter, and I'm going to point it to the front page of Twitter for that. The function I'm applying calls import on the remote URLs. Import automatically handles over 170 different formats, and HTML is one of them. This sub-option will import the hyperlinks that it finds on each page. By applying that recursively, it will follow each link to find more links to follow. Given time, it'll try and import the whole web, so we'll limit it to a recursion depth of 2. This function is set up to return a graph for page connections, and here is that visualized. Let's make that a little bit larger so we can see it better. And now you can see that one of the major hubs is this point here, is the jobs page, but it's not nearly as connected as their blog site. Well, let's do some actual analysis on that. Using the hit centrality command, we can find the hits hub and authority centralities for the graph. For that to be easy to interpret, we want to link the pages with their hit centralities, and this is what that looks like. Although what's interesting is to sort those according to the centralities, so we get a top 10 list of central pages. And having found the most central pages within the top 2 levels of this start, we might want to visualize, for example, the second most central page and how that fits into the graph as a whole. Like other examples in this talk, it's only this easy because we believe in making a single integrated system. If you happen to need something like graph tools, you don't need to stop work while you go and buy yet another add-on toolbox. It's right there waiting to be used. And, more importantly, is designed to work well with all the other built-in functions. Wavelet analysis is another one of those topics, which until relatively recently was considered quite specialized, despite its broad range of applications. We can use wavelets for image compression, for signal detection in time series data, and in this example, I will use them to remove noise from a sound. Like so many other areas of functionality, wavelet analysis is an integrated part of Mathematica. When we integrate functionality, we try to make sure it works smoothly with other parts of the system. So for example, the wavelet operations can be applied directly to sounds and images, as well as to raw numerical data. So let's get a sound. This is from NASA's Apollo 11 mission, the spaceflight that first landed humans on the moon back in 1969.
You will return safely to Earth.
I guess 60s radio technology had its limitations, as there's a lot of background noise in there.
You will return safely to Earth.
Well, our first step for dealing with that is to find the discrete wavelet transform of the sound. Despite the complex nature of the information that comes back from that transform, Mathematica can hold it all together as a single data object that we can continue to work with, for example, to visualize it. In this case, we would like to decrease the background noise level by performing a wavelet thresholding on the data. Again, I simply pass it that discrete wavelet transform data object that came back from the previous computation. And now we can transform it back into a sound simply by applying the inverse transform. And here's the new sound.
You will return safely to Earth.
Well, there's somewhat less background noise, and it certainly was easy to apply. Last but not least, let's end with a bit of fun by solving this maze. Here's a movie of the solution. Producing this movie calls on several of the capabilities that we've seen already. Solvers, in this case from graph theory, visualization, and some scripting to turn a sequence of visualizations into this movie. You might think that that would take a lot of code. But here is the entire solution. And most of it is just getting the details of the visualization right. The solving, the scripting, and the movie generation is all in this line here. And while we're here, let's make an interactive interface to this too. All such tasks are pretty quick and easy when you have the power of Mathematica behind you. Well, I hope you've enjoyed this talk. In this short speed date with Mathematica, we've touched on only a handful of application areas, and then in the most superficial of ways. And you can see information on many more of the industries in which Mathematica is used at wolfram.com/solutions.